Alright, today we're talking about permutations. We talked about combinations yesterday. Today we're talking about permutations. So a permutation, which I have highlighted here, a permutation of n different elements is an ordering of the elements such that one element is the first, one is the second, so on and so forth. So in this, unlike with combination, our order matters. And that is like the main difference between combinations and permutations, that our order matters. And the number of permutations is actually just given by oops, that's not a highlighter. N factorial. N factorial is the number of permutations. So if I think about rearranging these letters, A, B, C, D, E, F, in the first slot, because order matters, let's say, let's finish drawing these out. I have 6 options, right? I have 6 options of letters. Let's say I go with D. D is going to be my first letter. Now, since the order matters, I can't use it again. I just can't use it again. So now how many options do I have? I have 5 options, and I'm going to say F. Now I have 4 options. Use B. 3 options. Oh, that's a C. C. So we have 3 options here. For this slot, we have 2 options. I'll use E. Lastly, we have A options 1. And you notice, or 1 options, and that is A. Notice that right here we have 6 times 5 times 4 times 3 times 2 times 1. And that is the amount of different permutations that you're going to get. So 6 factorial is going to be what our the amount of ways that we can order these, where the order does matter. 6 factorial is equal to 720. Now, the permutations of n elements taken r at a time is going to be given by the following. Now, it's kind of going to look like something we've been, looking at the past few days with this NPR or NPIC-R, as we are going to say. NPIC-R. And the only difference from NCR is that in NCR and choose R, there's an extra R factorial down here. We don't have this in permutations or NPR, kind of like NPR news station. We are not going to use an R factorial. So now we're going to think about an example of some horses. We're going to go to a horse race, and we want to know how many different ways can we set up a podium with these 8 horses. So if I have 8 horses racing, 8 of them could come in first, right? So if 8 can come in first place. Now, if I already have 1 of them coming in first place, there are only 7 options left that could come in second place. So I have 7 options here. And lastly, in third place, I already have 2 of my options taken away. So in third place, I only have 6. You'll notice that this is, these 8, 7, 6, it lines up perfectly with if we would use our formula here. So let's look at NPR for this. So we have NPR is equal to 8 P3. So we have 8 factorial over 8 minus 3 factorial. And what is that? We have 8 times 7 times 6 times 5 factorial over 5 factorial. And hey, would you look at that? Our 5's cancel out, and we have 8 times 7 times 6. Oh, crazy occurrence. 8, 7, and 6. That is incredible stuff right there. Look at how cool that is. So this then equals, what's this equal? Oops. 336, not 5. 336. There are 336 ways that these horses can come in first, second, and third. So that's quite the number, and we could calculate that super fast. I mean, this took, like 3 seconds. We can calculate that super fast. So now, with that being said, suppose a set of n objects has one-of-a-kind objects, or I think I didn't zoom out enough. There we go. I was going to say, I thought I was missing something. So suppose a set of n objects has n minus, or has, oh my goodness. Suppose a set of n objects has n1, this comma's messing with me, has n sub 1 one-of-a-kind objects, n sub 2 of another kind, so on and so forth, all the way up to n sub k. It's going to look like this. So our set of n objects has all these little subsets with a different object. Think of it kind of like maybe if we put a bunch of marbles in a bag. So this n would be our total marbles. N sub 1 might be our blue marbles. N sub 3 might be our red marbles. So on and so forth. And this could be our yellow marbles, for example. The number of distinguishable permutations of the n objects is given by the following. We have n factorial, so this is like the total, essentially. This n factorial over n sub 1 factorial, n sub 2 factorial, all the way up to n sub k factorial. So this is a little bit, weird to look at. It doesn't make too much sense, so let's look at an example. Let's think about rearranging the letters of banana. So we can notice in the word banana that we have, of our A's, we have 3. I should probably write A's. We have 3. We have 2 N's. And then our B's, we have 1. So if we rearrange this and I swap this A and this A, what are we left with? We're left with B, A, N, A, N, A. Banana. It's still the same exact thing, but we are looking for distinguishable permutations. So that means that we can't just swap this A and the A, because that is not distinguishable. This banana up top is not distinguishable from this one. They are the same word. So we are going to use this formula to help solve. Now, so up top we have n factorial. So that is the total letters in our word. We have, I'm just going to put letters is equal to 6. So we have 6 factorial. That is going to be over our subcategories. So n sub 1 can be our A's, which is 3. N sub 2 are N's, which is 2. And lastly, N sub K, and K over here, this just means our last category. That's what that signifies. Is going to equal 1. So this then is equal to 6 times 5 times 4 times 3 factorial over 3 factorial times 2 factorial, because 1 factorial is 1. Do a little bit of fancy schmancy canceling. And we are left with 3 times 5 times 4, because this 2 cancels out here, and we get a 3, and that is left with 60. So there are 60 distinguishable permutations of the letters B-A-N-A-N-A, which is kind of cool, and we could figure this out really quick. If you look on page 611 in your textbook, it has them all listed out. And you can imagine how long it would take to actually go through and list all of these, different permutations. So that is all I have for today. We're going to go over a bunch of example problems in class, run through a bunch of them, and see what you guys got. So have a good one.